Says we got a lot of people online. Good. 6 people online. A few people in class. That's good. That's good. That's good. We're doing good. Today we start chapter 14. It's on multiple integrals. In 14.1, we are doing rectangular or box-like regions. Well, rectangular, yeah, or box. The way we do multiple integrals is, let's see, where's my highlighter? There's my highlighter. You start inward and you work outward. So we'll start with, you know what? Let's follow Roji Biv. Let's use red first. There we go. We do red first, and then this is as close as I have to an orange highlighter. We go outward, we do that integral next, and then we hit the outside integral. So we work outward. We work outward. When we're doing box-like integrals or rectangular integrals, we can do them in any order that we want. This is going to happen in 14.1. If we just have z equal, like it's just 2 integrals where we have an area, not a volume. This is like a volume over here. What we are effectively doing is we're integrating z, which is like a function of fxy. So we might have our box-like integral like this, rectangular integral, and we're going like from a to b along y and c to d along x. And I don't know what this shape is, but it might be doing something like this. Might be doing something crazy, where z is our function of f of xy, but we are integrating from a to b. That kind of slices this up into chunks. And we are like effectively doing a single box is like, where does it hit on this surface like that? And we're finding like, it may be the volume. We'll see in a later section what specifically volume is like. In later sections, like when we start tomorrow, we will have, not tomorrow, Tuesday. It won't be box-like. It still might be straight lines, but now X and Y isn't lined up perfectly with like values, or we might have an elliptical region or something like that. We're going to learn different regions. We'll probably start with just having skewed lines like that, where that doesn't look like it's, let's skew it the other way. Let's do that. Where it's not lining up like that's going to there, then we got something going on here. And like the lines we're doing changes. That's like 14.2. This is a whole different animal, but 14.1 is relatively straightforward. When we want to swap orders, as we'll do in problem 1, you'll see that we just change the order of integration. Let's grind through this one right here. We start off doing that. So don't ignore the outer integrals. Make sure they stay there. And here we are integrating with respect to y. We're going to treat x as a constant. So this becomes 5/2 y squared. That is 3xy. We are going from y equals 2 to y equals 5. And I have a dx. Someone smart pointed out to me earlier, ooh, that was a really big eraser. I don't need to have the y listed on both. It's a good idea to say what the letter is, at least when you have more than one integral remaining. That way you don't forget which letter you're doing, because we got to do that step next. We got to do it first. And we don't want to put it in for x. We want to put it in for y. So this will be 5/2 y squared I can do 5 squared minus 2 squared. I'll show you the other way to do this in a second. And then we have minus 3xy, and then the 5 minus 2. We still have the dx. This is identical to doing 5 halves, 5 squared minus 3x times 5 minus parentheses 5 half. Let's not use parentheses. Let's use a bracket. 2 squared minus 3x times 2. Notice that this takes up less space the way I did it. Those are identical things. This is the way you've learned it in the past. That's the way you learned it before. But by grouping, like all I've done is like I grouped this with this to make that. And then I grouped this with the minus hitting that to make that. You can do either form. If you want to write the longer version, you can. I think you actually make less errors doing the shorter version simply because it's easy to forget. If you don't do the parentheses, forget to distribute the negative to both of these. I happen to like the top version. And probably I have not used to seeing it, so I'm going to use that a lot. 5 squared minus 2 squared is 25 minus 4 is 21. 21 times 5 is 105. And then we got 105 over 2. And then I've got 5 minus 2 is 3, and we multiply that by minus 3x, I've got minus 9x. Straightforward so far. We finished our integration. I have 105 over 2x minus 9 halves x squared. And that is all being evaluated from -1 to 2. And do the pattern I did before. This is actually easier if you recognize those are both 3. You could write this as 3 times 105 over 2 minus 9 halves. But let's say you didn't. This we could combine directly. And it makes this a much quicker problem. But if you don't recognize that, we have 315 over 2 from the first number. We have 27 over 2 from the second. That is 288 over 2, which is 144. Any questions? So you work outward, inward, going outward. Start on the inside, work outward. It's kind of like the opposite of the chain rule in direction-wise. Chain rule, you keep going inward and doing the integral or derivative of what's going on the inward. This is like going the other direction, but like obviously integration is not the opposite of the chain rule. It's just direction-wise. Then we're going to take a look at it. Let's change it and let's put the 2 and 5 on the outside. If you like it, you can nestle the letter that you're integrating with respect to in the little dish right there, the little cup. The 5y minus 3x doesn't change, but that allows us to change the dx and the dy. And sometimes you'll want the dx, sometimes you'll first, and sometimes you want the dy first. Again, we will start on the inside. We are integrating with respect to x, so that is 5xy minus 3 halves x squared. And we're going from x equals -1 to 2. Still have our dy. Oop, that's 5y right there. The y is not changing. The x is changing right now. 2 minus -1. And then I have minus 3 halves. 2 squared minus -1 squared. I'm looking at 2 minus -1 is 3. 3 times 5 is 15. So 15y minus 2 squared minus -1 squared. 4 minus 1 is 3. Times 3 halves is 9 halves. All right, finish integrating. I have 15 over 2y squared minus 9 halves y from 2 to 5. You know what? I'm going to make the math a little bit easier on myself and factor out a 3 halves first. I think the math will get easier if I do this. I have 5 times 5 squared minus 2 squared minus 3 times 5 minus 2. Twenty-five minus 4 is 21, times 5 is 105, minus 9. $96, which is 3 times 48 is 144. Yeah, it was easier factoring out 3 halves. I didn't do that this morning. A little bit easier, huh? Same answer. So you should be able to change the order and still get the same answer. As I was showing earlier, when we have like weird things like in 14.2, it's not as simple as just changing the order because oftentimes we'll have variables in the limits of integration. And so we got to be real careful with that. We'll see that on Tuesday though. 14.1 is relatively straightforward. Any questions on that one? Ray's still writing. I want to give her a little bit, another second. Are you good? Okay. All right. So this is where I've got like z equals f of x, y. And I don't know what order I want to do yet, dx, dy, or dy, dx. So it might like help to look at like how would I integrate this? We might be able to do integration by parts, but like for me, integration by parts is always like a last resort because that's more work. Quick thing to check is doing like a u sub. So let's say like the u equals the exponent xy squared. And while we're doing this, let's ignore partial derivatives. Let's just say the derivative, if I do the derivative of x, y is a constant. So like du dx, if we do it with respect to x, would be du equals y squared dx. And I don't have a y squared out front. I don't like that version. What about with a dy? If I do a dy, I have 2xy dy. And I have an xy out front, so this is doable. It's going to be better if I rearrange that, like put the 1/2 or the 2 over on the left by dividing by 2. So I'm going to do dy on the inside, which means I'm going to do dx on the outside. This will be my x. We'll go from 0 to natural log of 2. Here I'll do my y from 0 to 1. And I'm going to rewrite this in a better order so we can see how it subs in. I'm going to put the xy with the dy. Hopefully we can see that like this right here matches this right there. So we're going to sub that in when we do the u sub. And the u sub is going to replace that. So you have two options. One of them is sub it in and make sure you leave this as, and you're better off saying y equals 0, y equals 1, e to the u. And then I'm going to say like 1/2 du. I know we can move the 1/2 in a second, but I'm showing our two setups. We can do that. And you very much, if you do not put, if you decide to not change the limits of integration, you better put the letters in the limits of integration. You better say y equals 0, y equals 1. If you just leave 0 and 1, you're going to get fucking hit on points on the test when we get to that test.
Sometimes updating the limits of integration is messy in itself. So
sometimes, yeah, sometimes updating the limits is messy. It's going to be messy eventually, but sometimes doing the actual integration first kind of makes it look a little easier. So if you don't update the limits of integration, you definitely want to do that. The other option we have is we can update the limits of integration. When y equals 0, u equals x times 0 squared, which is 0. And when y equals 1, u equals x times 1 squared, which is x. So our other version of this is doing 0 to x. And I'm still having the 1/2 du. These two things are identical if we follow them through.
The 1/2? Would you be able to pull it to the very like out?
Oh yeah.
Or is it only for the fruit?
No, we're gonna pull it all the way out. A constant be pulled all the way out.
Or just double check.
It's funny because the morning class asked that question right at this exact same point too.
Because it's something that I'm thinking about. Like, can we do that?
Yeah, we're going to do it. I just want to make sure everyone followed where I was getting what. Yeah. Any conditions for what?
Like, does the integral have to?
No. As long as the constant is multiplied by everything on the inside. If you've got a plus sign in there, be careful. You got to pull it out of like both things kind of thing, or a minus sign, or split it into two integrals, and then you don't have that problem. As it is, we have no worries. We can pull that 1/2 all the way out.
The base integral rules, like, also you could flip the bounds of integration and make the function negative.
Yep. And if you do it on both of these, you could flip both integrals, having them both in the opposite order, and the two negatives would cancel, which is crazy talk. Why would you want to do this? Why would you want to go from a positive to a negative? This sounds like wrong. Nathan's like, we're doing it. This is how we're doing it on a fuck test. All right. So let's go through and integrate. Oh, blessed E to the U, how I love thee. I wrote X there. That should be a 2. All right. So doing some quick shit on the side, we have E to the X minus E to the 0. And hopefully after our discussion last week or earlier this week, everyone remembers E to the 0 is 1. And we keep going. This is going to be one of those situations where I go back to doing it the original way, doing e to the natural log of 2 minus natural log of 2. Exponents fuck me up when I do this. I don't want to fuck it up and get the wrong answer. Because if I try to do it in the same exponent, it's wrong. Then I have minus, and then we do the 0, 1. E and the natural log cancel out, just leaving us the exponent. And that is 1/2 times 1 minus ln of 2. If you leave it like that, that's fine. Or we do 1/2 minus 1/2 natural log of 2. Not too bad, right? 14.2 is less fun. All right. Now, we can either break this into two integrals and do them separately. I just think that's more work. But you can. If you want to do x sine y dA minus y sine x dA, you can break them into two different integrals, and you can fucking do them in different orders. You can do the dy and dx and dx dy in either way you want. That's an option. I think it's easier just to do it all at once. So let's walk through that. Do we want to have X on the outside or Y on the outside? Or better yet, which one do we want to get rid of first?
Maybe the X.
So let's get rid of X first. That works. So we'll have 0 to pi over 2 on the inside. That's the X. So the outside will be the 0 to pi over 3. And we're going to do dx dy. Okay, we integrated with respect to X first. So this is 1/2 X squared sine Y. Minus, no, plus Y cosine X. This is evaluated from X equals 0 to pi over 2. Then we have a dy. Ugh. So we're replacing the X here. I have 1/2 sine Y times, I'll do this in a different color. Pi over 2 squared minus 0 squared. And then I have plus Y cosine of pi over 2 minus cosine of 0. This looks like a wonderful pi squared over 8 sine Y. How about them apples? Plus, what is cosine of pi over 2? And what is cosine of 0? 1. So that just turns into minus Y, doesn't it? All right. The fun stuff. Becomes negative pi over 2 over 8 cosine of Y minus 1/2 Y squared. And that's all evaluated from 0 to pi over 3. So what is cosine of pi over 3? That's a 1/2. Minus 1 is going to give us a negative 1/2, right? And then I have minus 1/2, and that is pi squared over 9. I'm going to factor out the pi squared and maybe a 2 on bottom. This is going to give me 1/8 minus 1/9 on the inside. Makes the math a little bit easier to swallow. If I get a common denominator, multiply the first one by 9, the second one by 8. And we get pi squared over 2 times 72 is 144.
How is it that you factored out the pi squared over 2?
I grabbed it I took that one and effectively that one, and then this one and this one. And what it leaves behind is the negative 1/8 times negative 1, which becomes 1/8. And the negative 1 and the 1/9 becomes the negative 1/9. Believe it or not, there was another way to do this. We're not going to go through all of it. I'm just going to show you the setup because it's a good setup for the next problem. Obviously, we could have done the dy first, but that's not what I was referring to. We're going to split them. And fuck it, I'm going to keep the same order just to not have any fucking wonky shit going on here. And then we have a minus 0 to pi over 3, 0 to pi over 2, y sine x, again, dx dy. I didn't show this to the morning class because I showed it on the next step, but I think you might like it here. This is a function of x times a function of y. I have something similar going on here over here. Maybe I'll use different letters here. This is a function of y times a function of x. When they are multiplied together, strictly multiplied together, we can separate the integrals into two integrals multiplied together. I can break this down into the outside one is the dy. So 0 to pi over 3 sine y dy times 0 to pi over 2 x dx. And then minus 0 to pi over 3 y dy and 0 to pi over 2 sine x dx. When they are strictly multiplied, and f of x has no y, g of y has no x, and the limits of integration for both are constant. we can separate them into a product of the integrals.
Same for both.
Yeah,
Just no variables.
no variables in the limits of integration. Yes. No variables in limits. Which happens to be the scenario for the next problem as well. So I can write this as -1 to 1 tangent x dx times 0 to natural log of 2 square root of e to the y plus 1 dy. You may not remember this from calculus 1 or calculus 2, but if we have the limit or integral from negative a to a of an odd function, this is always 0. Odd functions are like when x to the n is odd, or trig functions like sine, cosecant, tangent, cotangent. If you integrate from negative a to a of x dx, you get 1/2 x squared from negative a to a, and you work that out, you're going to get 0. X is an odd function. While we're talking about it, as in case you didn't learn it before, if you have negative a to a of an even function you're integrating, this is like having y equals x squared. And you're going from negative a to a. The areas along these two are the same. This can be written as 2 times 0 to a of the same integral. We have that here. We have the odd version here. So this is going to equal 0. But we can walk through the steps and show you real quick, just to, in case you're like, no, that you're full of shit, Mr. Jones. Let's see it in action.
Function is symmetrical about the y-axis, and then an odd function is symmetrical about y equals x, correct?
Yeah. So tangent is sine over cosine. You probably don't remember the integral of tangent x. So let's write it as sine x over cosine x. I'm not going to write we'll do that one later if we need to. If you do a u sub, this becomes negative integral of 1 over u du, and we're going to change the limits integration. When x equals -1, u equals cosine of -1. When x equals 1, u equals cosine of 1. Cosine is an even function. I didn't mention the even functions. This is when x to the n, that's even. Or for the trig functions, it's cosine and secant.
So it just goes with one.
It's just cosine of 1. Excellent. So this is effectively negative cosine of 1 to cosine of 1, and we don't have an interval. When you plug it in, it's 0 wide. So 0 wide is 0. This happens for even functions. If it's negative on the inside, it becomes positive on the inside. As a quick reminder, odd functions, like if I had sine of -1 or sine of -u, that's the same thing as negative sine u. You pull the negative out for odd functions. On even functions, it just goes away. So since this is a big fat 0, and this has got a limited region and nothing's going to infinity, this is not infinity. When it's 0 and infinity, you gotta like go which one's winning kind of thing. We're good to go. This is 0. We have 0 as our answer. Anyone need that up longer? I don't know who's still looking and writing. Okay. So this says we have the first octant, which is where x, y, and z are positive. It says we are blocked in by the plane y equals 4. I'm not for the second class, but I'm here now. So that's y equals 4. We kind of got like a plane right there. I got like a plane. Then we got this function, and like it might be easier to figure out what's going on by plugging in values. And I think actually plugging in values that make the fractions go to 1, easiest. So if I say z equals 5, this turns into x over 3 plus 5 over 5 equals 1. X over 3 equals 0. So x equals 0. When z equals 5, x equals 0. Which is true anywhere along that line. That's the line 0, y, 5. And if I do where the other fraction goes to 0, when x equals 3, I've got 3 over 3 plus z over 5 equals 1. We're going to get z equals 0, which has that point right there. And we're kind of doing that line. Which means this is like making a plane like that. If I come over here, I can do that. And if we trap this all in, I got that line, I got that line, I got that line, I got that line. For the plane y equals 4, we have that. And it's like our upper surface is this part right here. So the function we want to integrate, we want this as z equals a function of f of x, y. So we're going to solve this for z. Or fuck it, let's leave the 5 factored out. That might make the math a little bit easier in a second. What we're effectively doing is taking a little block right here and we are integrating that down to the plane down below. And as we do x and y, like it collapses and we get all of this like stuff. It looks like y is between 0 and 4 and x is between 0 and 3.
That's just 1/3 x.
What? You just multiply by 5 on both sides. Go from here to here, you multiply by 5.
Yeah.
So that's all I did. And I changed x over 3 to 1/3 x because I hate having. I'm not a big fan of the variable on top of the fraction. Unless there's a lot of shit on top, then I don't fuck around, but like, I don't know. Again, this is a function of, I can move this out. I can move the 5 out front.
Z equals,
This is a function of x only, no y. So like like we could say g of y equals 1 if we want. If we want to separate this, we can separate this. I didn't write my upper limits. Look at that. 4 and 3. I can break this down into the y, 0 to 4. I'll say 1 dy. You don't even need the 1, but I'm putting it there to make sure everyone's on board. And this is 1 minus 1/3 x dx. These are always a shitload easier when you can separate them. The limits of integration were constant. We didn't have x and y mixed anywhere. We got 5 times 4 minus 0 times 3 minus 9/6 minus some more zeros. There's a couple more zeros in there. Five times 4. This would be, oh shit, let's do this. This is 3 halves. And this is 6 halves. So times 3 halves. 60 over 2 is 30. You could also look at it geometrically. I have another minute. I'll just slap it down. Geometrically, that is a triangle. 1/2 base times height. The height is 5, the z component, and the width is the y, or is the x, which is 3. And then we have then we multiply that by the depth, which is the y value, which would be times 4. So 1/2, 3 times 5 times 4 gets you 30. But the integral is always going to work.
And that's just 5 units cubed or something.
Yeah. It's not always volume. When we do shit like density and stuff like that, stuff changes up. And we'll see how that works later on. That's it for today. Peace.